Hello and welcome back to this next part of coding up the LDSO Twitch version. We have left off at the dataset reader, and as you can see, currently there is missing a include for the Undistort.header file. And this is what we will do in this part. But before we start, I thought we should maybe just provide a short introduction into what we are going to create today. So let's take a look at the current data set that we have. And I have downloaded the sequence 45 and sequence 02 from the TUM monocular visual odometry dataset. So here you can see all the 50 datasets. And when we take a look at the images, you will see that the images are not perfect. They are somehow distorted, and we need to know how they are distorted to implement the whole magic that we need for the visual SLAM. We need to know how to project points from the image plane to another image plane, or how to back project them from 2D to 3D and back from 3D to 2D. I will keep this introduction relatively short. I just want to give you a brief overview of what kind of terms we will need to handle and what some of the magic words mean that we will stumble upon. So if we go back to the data set, you know the data set sequence 45. I have shown you this before. And if we take a look at the images, you will see that these images look okay, I would say, but still lines in the image that should be straight are not straight. They are somehow bent here. And even more extreme, this is even more extreme in the dataset sequence 02, for example. If you take a look at this image here, maybe one from a later point in time, like this, for example, you will see that here, this image is somehow completely different. It has this kind of circular shape. You have the straight lines once again, which are not straight in the image, and you have some kind of darkening around this image if you move closer to the borders. And these effects all can be summarized as the camera calibration. The camera calibration is usually a method to extract the parameters that describe such an image. And we have several of them, and there are several models, different models, which we can implement, and some of them are implemented in the original LDSO code base. So we will take a look at them here in this part. Let's make it a little bit more mathematical. If you take a look at the sequence 02, for example, you will have a camera.txt file, which we will work with in this part directly. So if you open that, you will see that here are some numbers. In this case, they are in the range from 0 to 1, which is not often the case. Usually they are similar to the image dimensions, but in this case they are given as a percentage, so we will need to handle them. So those are the camera parameters, which follow a very specific camera model. Next, you will have 3 more lines, of which the second line shows the image dimensions, and then you can have a line which tells you what should be done to those image dimensions. There could be an option which tells us this is full, or this is crop, or those 5 numbers in this case. And then you have some sort of a final image dimension, which should be the one that is applied or that is used after cropping the image, for example. So if you compare this camera calibration file with the one from the sequence 45, you will see there are some differences, and this one, I like this one personally better because it's not that much confusing. Still, you have those parameters here which range from 0 to 1. Then you have your image dimensions. Then, in this case, on the third line, you have this crop definition, and then you have your final resolution. This line 3 could also be full, for example, and those properties will have different meanings. So, for example, the full statement here would say that we do not want to crop the image, whereas the crop command would say we want to crop the image down into, for example, the dimension 640 by 480. So there are very specific settings here which we need, and those settings or those files, those camera calibration files, will be parsed and used in the undistorter that we will write next. Maybe a little bit more about the camera models. So if we look up camera models on the internet, you might be able to find this course notes from Stanford, for example. They explain what kind of camera models they have, and one of the standard camera models we have is, for example, the pinhole camera model. The pinhole camera model is related to a pinhole camera which you can create in reality, which tells us we have like an infinitesimally small aperture, so just a pinhole. And if you make such a camera, this would be a box, for example, you will see that if you have an opening into the box where you can look inside, you will see that this kind of camera will project a real object through this little, almost very tiny aperture or pinhole onto a film plane or an image plane, where you can see that the image is then inverted. In our case, when we are working with digital images, inverted images are not very nice to work with. So we can say we just take the film plane and place it in front of this pinhole, and this way it will not be inverted. So this is one of the tricks we do. But then, given this kind of pinhole camera model, we will just continue as usual. And we can express this pinhole camera model mathematically. If we take a look at the distances, the coordinate systems, and what is called a focal length. So the focal length is the distance from this pinhole to your image or film plane. If you know that, you can say, well, we can easily express the point x prime and y prime. Those are the points on the image plane. So the final image points you will see when you take the image. And they are related to one point, which is not p prime, but p, for example, which consists of an x, y, and z coordinate. And we have the focal length from our camera. If we multiply the focal length with the ratio between x and z and y and z, you will get the final x and y image points. It can be as simple as that. There are some particular problems with this definition, because if you take a real camera, you will see that the images usually will also have a depth of field. They will be blurry, for example, but this is not modeled in the pinhole camera model. But there are, of course, ways that we can model this blurriness as well. But we try to make those models as simple as possible, but still try to make them as close to a reality as possible. And the final definition, how we create this pinhole camera model, is that we assume we have this lens in the between the object and the film plane. We have this focal length, and then we define a matrix, which we'll come to later. But first, the image points that we just discussed, like this x prime and y prime, they will not be the final pixels, but the final image points, they will usually also be distorted. And they can be distorted if we imagine that we have a normal grid here. They can be distorted by either a pincushion distortion or a barrel distortion. There are also other distortion models, but those are the most common, I would say. So if you take a photo of a grid, you will see that you have this grid distorted when you take the image. If we compare that with the images from the data set, so for example the sequence 02 again, you will see that if you have an image with a grid, let's take this door for example, you will see that this grid in this case has a barrel distortion. So it is looking like a barrel and not like a real straight line preserving door, for example, that is imaged on the sensor. So this geometric camera model that we have just discussed, like the pinhole camera model, this handles the kind of geometric distortions or geometric projection onto our image plane. And the distortion model for example, the barrel distortion and the pincushion distortion, which I have shown here, there are different distortion models for that. So if we take a look at that, we have first, as I just discussed, the field of view. So basically, what kind of camera are you using? Are you using a wide angle lens or a telephoto lens? This will result in different projections. So for example, if the focal length is short, you will usually have a large field of view. And if the focal length is longer, then you will have a smaller field of view. So this field of view is one additional aspect that comes into play. So you do not only have this idea of distortions and the pinhole camera, but you also have the idea of field of view. So if we take a look at this image, for example, again, I would say this is a rather large field of view. So the camera usually has a short focal length. There are ways to calculate that. We will not go into detail, but we will take this as given. And there is also the other aspect of the distortions. So if you model a camera, here's a nice website that explains it a bit more. We can have, as I just explained, we have this grid, for example, and this grid can be projected in different ways. So we can have this pincushion distortion, which will take this grid and create this kind of shape here, like a pincushion, or this shape, which looks like a barrel distortion. And those distortions are called radial distortions. So they are just, if you imagine you have this whole object here, and you imagine this center point, they will have an effect mostly around a circle, I would say. So of course, if you increase the barrel radial distortion, you will have more of a circle, whereas if you increase the pincushion radial distortion, you will have more this pincushion shape here. Now there are, of course, models to define that mathematically. Here is an example for the tangential distortion. You can also say it's a decentering distortion. So different to the radial distortion, the tangential distortion will shift your image in a specific region. At least it will look like that. So we can see the center square here. It is not shifted, but the borders are more shifted in a specific direction. In which direction they are shifted can be defined using this specific radial tangential distortion model, for example. If you combine the radial and tangential distortion, you will, for example, get something like that. So a grid that was photographed will be somehow shifted and scaled and distorted in general. Now we do not only have this this kind of distortion model that combines radial and tangential, but also the what is called, let me quickly look that up, for example, Brown-Conradi distortion model, or one model that is used in the LDSO, which is the Canala-Brandt distortion model, which is from 2006. And here you can see how this is computed. So you have several parameters, K1, K2, K3, and so on and so forth. And those parameters will define your, let's say, your radial and tangential distortion or the deviation. Okay, there are also other distortion models, but the radial, tangential, the Canala-Brandt model, this one here, the pinhole camera model, the field of view model, those are the models that are used for the geometric camera calibration in the LDSO, and they are very common in other Visual SLAM implementations. Now, we do not only have the geometric camera calibration, but we also have the photometric camera calibration. I found this slides from one user from, let's quickly go to that. Unfortunately, there are ads here, but Ali Abdul Zara, he created those slides, and in these slides there is one depicting the process from the scene radiance, so basically like your real world lighting. This scene radiance is passed through a whole range of processing steps, I would say, starting from the optics to the aperture and the shutter and the camera body to the sensor, which then performs specific operations like a gain, like let's say image brightness correction, then an analog to digital converter where you have your raw images, and then other operations which compress the image. And if you want to model the image intensity correctly, you need to know for every camera how the geometric and photometric properties of your camera, what they are. So we need to define several parameters to, let's say, undo this camera specific image processing. Let's take a little bit more about what happens here, not in detail, but with visual examples. So for example, here on this slide, you can see that there is a radiometric response, which is usually a curve. And this curve, for example, can be seen in the dataset. If you take a look at the pcalib text file, you can see that there are values from 0 to 255. And for each step, for each intensity, you will have values from which you can draw this kind of response curve or gamma correction curve. So this is one thing that is included in the photometric calibration, but there is also another nice thing, that is the vignetting. And the vignette is, if you take a photo, you will have this kind of circular border. And the reason why we would, for example, want to model this kind of vignette is if we want to stitch the images. So if you have several images taken from a camera, you can see that the images, if you superimpose them, for example, they will not have the same brightness. And in order to correct the brightness, which you can see here in the in this part, you will have those not very beautiful non-continuous image brightness areas or regions. If you correct for the vignette, for example, you can have one nice image that is stitched from multiple images, where you can see that the image brightness is almost constant across the whole final composite image. So there are many things we can discuss here, but I just wanted to give you this kind of overview of what terms you will see when we work with the Undistort class, which we'll implement in this part, and somehow get a feeling of why we want to do what we are doing in the implementation. And the main goal is, once again, we have multiple images coming from a camera, from a monocular camera, which you can see here. And we want to be able to project a specific pixel, so for example, the one here on this corner, onto another image. That's why we need the geometric camera models. And then we want to compare image brightnesses. We want to basically, in this case, we do not want to stitch them, but we want to compare image brightnesses. So a pixel which is in this darker area, close to the border of the image, we want to be able to compare this kind of pixel to one in a later image that was taken at a later time step, with a specific pixel in a later image, and we want to compare the brightnesses, and they should be, ideally they should be the same. They should be the same in intensity, but the camera will do something with the image intensities, and therefore distort them. And we want to undistort those images. We want to undistort this kind of geometric distortion here in the images, and we also want to undistort the pixel intensity distortion in the images. So this is the goal of this part today, and we will see what we need to do to actually undistort the images that we have. Okay, so let's go back to the code now and let's take a look at what we have so far. So we have implemented the internal functions here and the front-end data structures, like the image, the minimal image and the image and exposure, which will hold the image data for us. But now we need to do something with the image data, which is defined in this Undistorter file. So we need to create this file. So let's do that now. We go to the front-end directory and create a new file, which is called Undistort.h. So this will hold our both the geometric undistorter and the photometric undistorter. And this header file will have a corresponding source file. So we go to the source directory, to the front end, and here we will also create a file which is called Undistort.cc. So we have the header file and the implementation, and we will create both of them now. Okay, let's start with the Undistort.header file, because this will give us a brief overview of what we are actually creating and what we need. We start again with a pragma, which tells us that we want to include this file only once. And then we will create a header guard, if not defined, LDSO Twitch Undistort.h. And of course, if it's not defined, we define it. And in the end, we end the if of this specific file. Oh, this should not be in the CC file, but this should be in the header file. I'm sorry. Let's put it in the header file, because we will start with writing the header. Now we need to, as usual, include some other parts from our code and the eigen library, which we'll start with. So we include the eigen/core, which will give us access to vectors and matrices and all of this useful stuff. Next, we will include from our front end that we already have the file image and exposure.header file. Next, we will also include our numeric types, numtypes.h, and we will also include the minimal image.header file. So the Undistorter that we will code up here, it will get all of our images that we have and undistort them. It will do that if we want that to happen, but usually if the images are undistorted, it will go through each image and undistort the image. Okay, next we create a namespace. As usual, it's called LDSO. And in this namespace, we will create two classes. We will create a photometric undistorter, handles gamma response, vignette, and I think something else as well. Let's keep it like that. And we will have a geometric undistorter, which handles the pinhole, the canala brand, the FOV, so field of view, some equidistant, and what else? I think I'm missing something again, but all of those camera models, not only camera but also and distortion models. So we have the camera models and the distortion models, which will be handled here as well. Okay, let's start with the photometric undistorter. So we define a new class, which is called photometric undistorter. And in this class, which should be finished with a semicolon, we'll have a public scope and a private scope. And in the public scope, we define an optimization for the eigen library, which is the eigen make aligned operator new. And then we will define the constructor and the destructor. So the constructor is, of course, the same name, photometric undistorter. And this constructor takes in as argument a standard string, which is the file, which should be, in this case, I think, the image file, if I'm not mistaken. Let's see later. Then you have a standard string which contains the noise image. Then there is a standard string for the vignette image. And then there's width and a height. And this is so far the definition of the constructor. Next, we also have the destructor, which is called the same, photometric undistorter and semicolon. Next, we will have a method, which is a templated method. So we write template, type name, and the type name will be t. And the definition of the method is process frame. It takes in a pointer of the templated data type, and we call that first parameter image in. So why is it a templated function? Because if you recall from the minimal image definition, we have several minimal image versions. We have a float array, we have a vec3f array, an unsigned char, unsigned short, and we want to have the undistorter being able to work with all of them. So that's why we are using a template here. So next we have a float, which tells us the exposure time. And then we have a float factor, which is equal to 1 if it's not supplied. And this will, as far as I know, for example, scale down the image. Okay. Oh, sorry, I think this will scale down the image intensities, but there is also a factor later in the geometric undistorter which will scale down like the geometric image dimensions. Next we have a method which is called unMapFloatImage, which takes in a float pointer of the image and before I forget, we can also add some documentation to this process frame method, namely that this one removes readout noise and converts to irradiance. So if you remember, we have the radiance coming from the scene, like basically our scene lighting, and we want to get the irradiance. Then there is a comment affine normalizes values to 0 less than or equal to I less than 256. Then we have raw irradiance, which is defined as A times I plus B. And the parameters A and B, they can be applied to change the contrast of our image and the image brightness. And these parameters A and B, we'll see them from time to time, and I think we also saw them in the example code. Let's quickly switch to the example code. I think there was something about the A and B here. Here, for example, this one. If we supply the mode, the photometric mode, we have a setting for the affine parameters, whether this A and this B should be optimized. So if these are -1, we fix them, and if they are greater than 0, we optimize them. If they are greater or equal to 0, we optimize them. So here, if we supply perfect images, that is, for example, images created in a simulation in Blender, for example, we do not need to have this photometric calibration. But if we have real images, then we can supply a photometric calibration, which would be this part here. Or if we do not have a calibration and we want to optimize this A and B parameters, and the A and B are used when we change the image brightness. Or let's say the irradiance. Next, the output will be written in the output variable. So this is the explanation for this process frame, so that you have a rough idea of what is happening here. We want to remove the readout noise, and we want to convert to the irradiance, which we can do with the photometric calibration, with the gamma response curve, and with the A and B parameters. Okay, next we will have a public image and exposure data type, which is called output. Then we will also have a method which will return a float pointer, which is called getG. And this will be defined directly here in this header file by, let's do it a different way like this. If not valid, then we want to return 0, and else we return G. Okay, G is not defined yet, and valid is also not defined yet, but this will be defined in a minute. Namely, if we go into the private scope, here we will define a float array called G with the dimensions 256 by 256. And then we have a G depth integer. Then we have a float pointer, which is called vignette map, and another float pointer, which is vignette map inf. So as you have already seen in the, I think it was the image and exposure, if I'm not mistaken. Or in the dataset reader, probably. No. Not here as well. I'm looking for the camera calibration, maybe global calib. Ah, yeah, here. Okay. Here in the global calib header file, we have written the pinhole camera model, which consists of a focal length in X, Y, and a principal point in X and Y. And here we have the inverse pinhole camera model. So we had the inverse model for the geometric calibration. And now we can see the same is happening here with the vignette image, for example. And we can also do the same with the gamma response, or G. I think this is the gamma response. But I don't know why this has this dimension. So 256. I would expect it to only have one dimension, because if you recall our pcalib text file, there are 256 values in total here. So if you count in the 0, and therefore I would expect one dimension to suffice here. But yeah, there is a second dimension, which I do not see at the moment. Okay, so after we have this vignette map and the inverse of that, we define a width and a height as integers, and a Boolean variable which tells us, is this valid or not? Okay, now there should be no errors here. And we have a definition of the class photometric undistorter. Next, in this class, we need to implement the constructor, the destructor, this process frame, and the unmap float image. The getG is implemented already here in this header file. And then this should be done. And next, we want to have a geometric undistorter. So we create a new class, and this is called Undistort, class Undistort, which also needs to end with a semicolon. And here we have a public scope, and of course later a private one as well. And in the public scope, we once again say that we want to optimize the eigen library. So we write eigen make aligned operator new. Then in this case, it seems that we do not have a constructor here. Okay, there's no constructor, but there is a destructor. Which is a virtual one. And that is because we are defining this Undistort class as, let's say, a base class. And we then implement specific variants of that for the different camera and distortion models. So we also define a virtual function, virtual void, for distort coordinates with const equals 0. And this distort coordinates will get coordinates in and will return coordinates, distorted coordinates, as the name suggests. So we have a float pointer to in x and a float pointer to in y. And we have a float pointer to out x, and we have a float pointer for out y. And we also have an integer n, which will probably mean something, a number. I'm not sure what it is at the moment, but the n is included here as well. Okay, next we will have a virtual const char pointer. This is the return type for the method get camera model type with a const equals 0. So this will also be implemented in the various camera model implementations that will follow. And next we have some inline definitions. So let's maybe add a comment here. Okay, the inline methods are inline const met33, and it's called getK, which is, for example, return camera calibration matrix, which is a 3x3 matrix in this case. There are also different definitions depending on whether you are using the homogeneous coordinates or not. Okay, get k is a const, and it will simply return k. Next we have an inline const eigen vector to I, which is called get size. And this returns an eigen vector to I of the width and height of, as I suppose, the image. Turn image dimensions. Let's write it like this. Okay, next we have a function inline and then a vec x, which can be an arbitrary vector of arbitrary size, a vector of arbitrary size. Get original parameter const. And this will return something that is called parse org. And as far as I understood, this is these are the calibration parameters, which depend on the camera model. So we will, in our implementation, take this camera.txt file and we will parse those lines. Those 4 lines, the camera.txt file will always consist of 4 lines. And the parameters that are included here, I think it's only the first line. This is what will be stored in this parse org variable. Okay, parse org, that's the name. We do not have this yet. And next, we want to return let's change this number 2 here to return cropped image dimensions. And here we want to return the original image dimensions, which should also be a 2D vector. Yes. So we define an inline method, inline const eigen, and I forgot a const here. Inline const eigen vector to integer, get original size, const, and now for the body, return eigen vector to I, and we create it from the WORG and HORG, which will contain the original width and the original height of our image. Okay, and then we also have a 5th inline method, which will return if calibration is valid. Or let's say if this undistort, if the undistorter is valid, rather. And here we write inline bool is valid, which is not const, which returns us valid, which is also a variable which we do not have yet, but we will create it. Okay, next we have the Undistort method, which will basically do the magic to our images, to undistort them. We will also template this method because we want to use different kinds of minimal images, like as I showed, the unsigned short, unsigned char, and the RGB image, and so on and so forth. So we create a template identifier here, template type name T. It will have a return type image and exposure, a pointer to be specific, and the method is called Undistort. It takes in a constant minimal image of this specific template type T, and this is a pointer to the raw image data, image raw. Then we have a float for the exposure, which is usually initialized to 0, and we have a double timestamp, which is also initially 0. And then we have once again a factor, float factor is equal to 1. Now this method is also a const method and will be implemented later. So here we can say those are our, what did we write here? Inline methods? Yeah. We have some prototype methods here. Will be implemented in the inherited classes. And the first one is the Undistort method. It will take image data, exposure, and timestamp and create an image and exposure object. It's usually a pointer, but we can say it's an object. I think it should be clear from that. Okay, next we have a static Undistort pointer as a return type, and we can this Undistort type will be returned when we call get undistorter for file. So we have a specific file which is given by standard string config file name. So the config file name in my view will be this camera.txt file. This one, for example. Next we have a standard string gamma file name. And next we have a standard string vignette file name. So this one let's say I'm missing the correct word here. Return undistorter, not base class, but the inherited class subclass. I think it's undistorter subclass. given a specific geometric and photometric calibration file. And then we want to load the photometric calibration. That is void load photometric calibration, which takes in a standard string for the file. Then we have a standard string for the noise image. And we have a standard string for the vignette image. And lastly, we also have a photometric undistorter, which we have defined above. So this photometric undistorter is contained in the geometric undistorter. So the geometric undistorter is, let's say, our the right data type that we will work with. So this photometric undistorter is called, it's a pointer, it's called photometric undist. Photometric undist. Okay, next we need to define all of those variables here. And this will be not in the private scope, but they will be in the protected scope. Why? Because if we derive this base class and create subclasses, we want to pass on those variables that we define here. And this will not be possible with the private scope. So in this protected scope, we define, of course, the integers: width, height, WH, WORC, and HORC, and also a W up and an H up. We also define an integer upsample, undist factor. So there's also an upsampling possible, it seems. And we also have a mat33, of course, which is the K matrix, which is our pinhole camera model, or let's say the intrinsic camera parameters. And we also have a vec_x parse org, which contains the parsed values from camera.txt. Not fugue file. Okay, from the file. Then we have two booleans, bool valid and bool pass through. What this means, what it means to have an undistorter valid, we will see that, but pass through is, I think, that we just do not want to undistort the images, which would be the case if we have perfect images generated from Blender, for example, some synthetic images that do not need to be undistorted because they are already undistorted because they are perfect. Next, we have a float pointer for remap X and a float pointer for remap Y. And then we have some methods. For example, a void apply blur noise. which takes in a float pointer img. It is a const method. Then we also have a void make optimal k and now crop, or the same, not with crop but with full. And lastly we have a void read from file, which takes in a const char pointer to the config file name. And we also have an integer n parse, which is the number of parameters, I would suppose, and a standard string prefix, which is an empty string. Okay, and that's it for the definition of the base class for the Undistort class. And next we need to define the individual subclasses for the Undistort blueprint, let's say. Okay, let's turn on the music. Which is by the way powered by no copyright sounds. Thanks for that, by the way. Okay, next. I think you cannot really hear the music. It should not be too loud, of course. Okay, as I wanted to say, next we have different classes for the individual camera models. That is, for example, we have a class which is called Undistort.h, which inherits from the class Undistort, from the base class. We will also have other classes. We will have an Undistort red 10. Let's maybe name them field of view undistorter. We'll have a radial and tangential undistorter. Radial and tangential. Next we will have an equidistant undistorter, which is called Undistort equidistant. We'll also have the usual pinhole undistorter, Undistort pinhole, and I think we will also have one more, which is the Canala Brand Undistorter, which is Undistort KB. So those are our subclasses which implement different camera and distortion models. So the dataset provided to our LDSO Twitch version, they can be of camera type field of view, red 10, equidistant, pinhole, and Canala Brand. Now what is happening inside of those class definitions? Let's create the body here. First of all, we'll have a public scope. And we will have, in this public scope, we will have the eigen optimization, make align operator new. And this is something we will have in every class. So let's copy it to every class, like this. And let's continue with the Undistort field of view version. Here now we will have a constructor. And we'll also have a destructor. And we will have methods for let's quickly summarize that. Yeah, let's write methods for distorting coordinates and getting the camera model type. As string, or let's say const char array. Okay, and this will be included in every definition of every type. That's why I will copy that as well. Okay, now we need to fill in the definitions. So for the field of view, the constructor will be called Undistort.fov, and it will take in a const char pointer to the config file name. Bool, no prefix. Then we will also have the destructor, Undistort.fov, and the methods will be called void distort coordinates, which will take in a float pointer in x and a float pointer in y and a float pointer out x and a float pointer out y and an integer n with the modifier with the modifier const override, because we are overriding the distort coordinates method from the undistort class, which is defined here. They will be implemented by inherited classes. So this one, and as you can see, there's another one, this const char get camera model type. So we can copy that and put it inside this definition of the undistort field of view type. But this time we will put in the definition of this method inline. So inline const char pointer get camera model type, and the modifier is still const override. But we add the definition here with return the string FOV. Okay, let me quickly check something. So here in the Undistort class, I was missing a semicolon, which is a little error. And I need to, of course, add that to this inline definition here, which was not done in the original code, but to keep it consistent, I hope I will not forget it. Okay. Now we have the Undistort field of view here. I'm just checking if I have not forgotten something. But this should be okay. The rest will be quite similar. So I'm thinking about copying that. And I think I will do that. So let's just copy that, even though this might create some errors. I hope I do not forget something. So this undistort red 10 will then return not FOV but red 10. The undistort equidistant will return equidistant for the model type. The pinhole will return pinhole as the model type, and the canala brand will return KB as the model type. Okay, but the constructor and destructor will need to be defined differently. So let's go to the rad and ton here. And now let's rewrite this from scratch. Undistort rad ton with a const char pointer to config file name and a boolean with no prefix. And the destructor will be undistort ratan, like this. Okay, the rest is fine. Just double checking here. Okay. Let's continue with the equidistant undistorter, which is undistort equidistant. This will take in a const char pointer to the config file name and the bool with no prefix. And the destructor is simply undistort equidistant. Like this. For the pinhole camera, we'll have undistort pinhole. Again with const char pointer config file name, bool no prefix, as we already did with the other ones. The destructor is undistort pinhole, like this. Then we have distort coordinates, which is okay, and we have the get camera model type as pinhole. Okay. there's one difference here for the Undistort pinhole model. That is, it will have a private scope which contains a float array, which is called input calibration, and it has the size 8, which is how many input calibration parameters it can take. So we need to account for that. But this is the only difference in this Undistort pinhole camera model. And the rest with the Canala Brand will be the same as usual. So we go to the constructor, write Undistort KB, which takes in a const char pointer to config, file name, and a bool no prefix. And the destructor will be the same, Undistort KB. And this should be it. Let me quickly double check. Okay. Seems to be everything. That's why we can delete this space, and the Undistort header file is finished. Good. So now let's continue with the Undistort.cc file. So the Undistort.cc file, before we forget, will need to be included in the CMake lists file here. So in the source directory, we have a CMake lists.txt file. And here we need to add that definition of the Undistort object. So let's put it here, maybe in front of the image definition. So we have the front end, and in the front end we have the Undistort.cc file. Okay. In the implementation, we start with including the necessary files. So let's include the S stream, because we will read in files. And because we are reading in files, we need also an F stream and an IO stream. This is for data parsing, or let's say, yeah, data parsing is okay. Then we have operations on, let's say, vectors and matrices. For this we need, of course, again, eigencore and the iterator. And then we also need to include our custom files. That is include, of course, the settings.header file, because we will have specific settings for the photometric undistorter and the geometric one as well. Then we have internal global funcs that we have prepared. Then we have front-end Undistort.h, and we have the front-end image readWrite.h. We are using a namespace here, using namespace LDSO internal. But we are also defining a namespace, which is LDSO. And in this namespace, we now want to, let's add comments, implement photometric undistorter constructor. This will be a big one, I think. Then we have the destructor. And we also have the methods. For example, unmap float image and process frame. And the process frame method will be implemented 3 times due to various templates we can use for the images that will be output. Let's add it here. And then we have to implement the distorter. No, distort, I think. Yeah, distort. Which is the geometric one. And here we have to implement the destructor. Then we have to implement the method for get undistorter for file. And also the load photometric calibration method. And also the undistort method. And there are also 3 types for that. Three times due to different image types. Then we have the undistort method called apply blur noise. Then we have the make optimal K crop. And of course also the make optimal K full. Then we also want to implement the method read from file. And then, after we have read from the file, we want to implement the individual undistorter types. That is, we want to implement undistort FOV constructor, and of course also the destructor. And then we have the method distort coordinates. And then we have the same for the red 10 model. After the red 10 model, we have the equidistant model. And lastly, we have the Undistort KB constructor and destructor, and the distort coordinates of this one. And it was not lastly, but we also have, of course, our very important pinhole camera model, which is the main one that is usually used. Here we have the constructor, destructor, and the distort coordinates method, but this is everything. So as an overview or as a summary, this is a summary of what we need to implement. Okay. Let's maybe thinking about how to organize this code. Maybe like this. And now we can copy these comments. Implementation. Here's the implementation. I know it's maybe not the most beautiful way to explain that. I'm just trying to write something to get my thoughts sorted. Okay, and not to get confused. That's very important. Let's take a drink. And let's start now. So the photometric undistorter, the constructor of this class, will be defined as follows. We have, of course, the photometric undistorter class, and within this class we have the same name, the constructor. This constructor takes in a standard string for the file, a standard string for the noise image, a standard string for the vignette image, and a width and a height. The body will now look like this. We say in the beginning that this undistorter is not valid, so valid equals false. We initialize the vignette map as well, vignette map to 0, and the vignette map inverse is then also 0. We set W to W underscore, and we do the same with the height to height underscore, and the output is equal to new image and exposure from W and H, and we check if the file is equal to the empty string, or what is happening? Here, okay, vignette image. So if the file or the vignette image, they are equal to the empty string, then we print no photometric calibration, exclamation mark. So if we do not have files provided, then we can assume that we do not have photometric calibration, and there's a colon missing. Okay, now we are starting to do some stuff. First of all, we read the G, which is the gamma response, I would say. If this is really the case, we will see that in a minute. But we open a standard IF stream. Where we define first a name, standard if stream f, input file f, then file.cstring, so this file will be opened, and then we say, hey, we are currently reading something, that is, we are reading photometric calibration from file which file? File.cstring, and this time we do not have an exclamation mark but only an end line. Okay, next we check if the file is not good. Then we return that the photometric undistorter tells us could not open file. Exclamation mark and end line. And we need to return now, because if we cannot open the file, then of course we cannot do anything with that. Okay. Next we continue with parsing the which file, gamma response. We can write the scope operator to separate this section visually. And here we define a standard string which will contain the line. Then we will get line from f and put it into line. And then we create an iString stream object, which is L1I of line. And we create a standard vector of type float, which we called the gvec. And it's equal to standard vector of type float and we put in a standard iStream iterator of type float with L1I. So this is the line iterator. And as a second argument, we define the allocator to be of the same type, standard iStream iterator of type float empty. So like this. Okay, now we have the gvec defined, and next we get the gdepth, which is an attribute of this class, and we set it to gvec.size. Okay, now this is expected to have size greater than 256, greater or equal, I mean. cpcalib.txt file. Okay, so we have to check that. So if gdepth is less than 256, then we want to standard cout photometric undistorter invalid format. Got so many entries like int gvec size, entries. Let's put it in a new line. Entries in first line. So this L1 means line 1. This will get important later as well, because we will have L2, L3 and so on. But at least for the first line, which does not make sense for the photometric calibration, I think, here. So the pcalib only has one line, but this will be important for the camera.txt file, for example. But here it doesn't make a difference if we write L1 or just line or something. Entries in first line. And this is expected at least 256. Standard end line, and we need to return. We cannot handle that, so we need to return. Next we have a for loop. For and I equals 0, I is less than g depth and I plus plus. And with every iteration we say g at position I is equal to gvec at position I. Okay, so we basically fill in gObject by parsed values. Next we have a second for loop, which also is defined using int I, and the music has stopped. Okay, so here we have filled in the G object, and next we want to iterate again using the G depth, but this time -1. And in the code we'll check if G at position I plus 1 is less than or equal to G at position I. And if this is the case, then something is wrong. Namely, I want to print out photometric Undistorter G invalid. It has to be strictly increasing, but it isn't. And then standard end line. So there is an assumption or a constraint on this data in the pcalib file. I'm not really sure if this is the pcalib file that is passed here, but I'm quite sure about that. And that means that for every subsequent value, this value needs to increase until 255 usually. If this is vice versa, then this is invalid. Okay, so if this is the case, that G is invalid, we need to return from this method. But this is everything. Now we need to define some floats. Float min equals G at position 0, and float max is equal to G at position G depth -1. And next we have a for loop, which loops through with int I equals 0. I is less than g depth. And I++. It loops through all of those g values, g at position I, and sets them to 255.0 times g at position I minus min divided by max minus min. And this is to make it to, okay, this does not make sense, make it to 0, 255, and then 0, 255. Not sure what this should mean. Make it to, okay, it's clear that this is some kind of scaling here. What is max minus min? Let's quickly calculate that. So we have the minimum value, which is 0, and the maximum value, which is 255. 255 minus 0 is 255. And then we have min is 0. This will be simply the value, so we will have, for example, for the last value, we will have 255 times 255 divided by 255, which will return 255. Okay. Maybe, not sure. Maybe this is accounting for different file formats. For example, if we have a camera calibration which is not at maximum of 255. Yes, this would probably be it. So let me rewrite this to make it to be 0 to max. Maybe it should even work with min to max to 0 to 255. I think this loop is meant to do that. I hope I'm not mistaken, but we will not need to think about it in detail because our data set is already perfectly fine. Okay, so this is about this block. This is the parsing of the gamma response. Let's add here this pcalib.txt file. Again, I think this is the case. I'm not 100% sure, but it looks like it at least. And now I think I know why this undistort header file here, why we had this G array with 256 times 256. It's, I think, only accounting for some additional space, but we could of course just leave it like that and it should be fine as well. So I think we are talking about the gamma response here, but we will see that if we take a look at how the photometric undistorter is used within the constructor of the individual files here. Okay, but let's not get ahead of ourselves. So this scope. Okay, after this scope or this block, we add an if statement. If the setting photometric calibration is equal to 0, Then we... What is photometric calibration equals 0? Let me quickly look that up. Perfect images. Okay, I thought that. So what are we doing then? If we have perfect images, we do not have a photometric calibration, so we need to somehow initialize it. And this will be done with a for loop. For int I equals 0, I is less than g depth, I plus plus. And here we take the g object at position I and initialize it with 255.0f times I over float casted g depth minus 1. So, what does this mean? With perfect images, we initialize the gamma response to a linear curve, I would say, i.e. g equals I over n. So in the beginning it will have, let's say we make this this series 0 over 255, 1, 2, 3, and so on. So the first one will be 0, then we have a small fraction until we get to 1. 255, 255. Like this. Pretty simple. Once you understand it, of course. Now with the photometric calibration, we continue with printing that we are now reading the vignette image from vignette image.c string and no exclamation mark, but let's make a full stop and standard end line like this. So now we want to prepare the vignette image data types, which would be minimal image types with unsigned shorts. And this will be pointers to called VM16, and they will be populated with IO wrap, which we have prepared already, which provides us several reading or image reading methods. And we take the read image black and white 16U, so this is this one here, and we pass it the vignette image.c string, and of course this needs to be a call. Okay, but we also have a minimal image of type minimal image B, which should be unsigned char, I think. Yes, unsigned char, which is also a pointer VM8, VM8. And this will once again be called using IOWrap, read image, and this time we take the 8U version of vignette image dot C string, like this. And next we fill in the vignette map with new floats using the width and the height. And we do the same with the vignette map inverse. Fill vignette data types. Read vignette images into minimal image types, both 16-bit and 8-bit. Not sure why this is being done using those two variants, but we will see. Okay, next we want to fill up, not fill, but initialize the vignette image data. So if we have VM16 not equal to 0, then we do something. Else, if the VM8 is not equal to 0, then we do something. And else, we do something else. So here we check whether or not the image data was loaded, and we do different things with the different data types. So for the 16-bit image, grayscale image, we check if the VM16 width is not equal to the width, or VM16 height is not equal to the height. In this case, we print that the photometric undistorter has invalid vignette image size, and we got VM16 width by VM16 height and we end the line. So like this. Wait a second, we are also expecting something. Of course. By, and then expected expected, oops. Expected W and H. And we add this X here. Okay. Something like that. So if this happens, then we want to check if VM16 is not equal to 0. Then we need to clean up, delete VM16. And we do the same with the VM8. And then we return. So else we create a float max v is equal to 0. And we loop through integer I, and I is less than W times H. So width times height, I plus plus. And here we check if VM16 at I is greater than max V. And if this is the case, then we say max V is equal to VM16 at I. So we update the max V value based on the parsed image intensity, I would say. So max V is the maximum vignette pixel, I would say. And this needs to be stored, because later we want to compensate for that. So after this is done, we make a second for loop with int I equals 0. I is less than W times H, I plus plus. And here we say vignette map at the position I is equal to VM16 at I divided by the maximum value. So here in my view we normalize the values. Normalize values to be in range 0 to 1. Let's keep it more, let's make it more concrete. Normalize vignette intensity values. Okay, something like that. Okay, and this is the case for VM16. Now the case for VM8 is probably almost identical. That's why I will copy it from the VM16 and paste it here. But of course we want to check VM8 width is not equal to width, and VM8 height is not equal to height. Then we print photometric undistorted invalid vignette image size got. Then we need a VM8 width and VM8 height. and we have expected W and H, and we delete both of those vignette images and we return. Next we have once again float max v is equal to 0. Then we step through the width times height and we check vm8 at I is greater than max v. And if this is the case, max v equals vm8 at I. So this is fine. Next we have this loop which fills in the vignette map, and of course using vm8 at I divided by max v. Okay, after that, if we do not have either vm16 nor vm8, we want to print something to the screen, namely photometric undistorter invalid vignette image. End line. And we still need to clean up, so if vm16 not equal to 0, then we delete vm16, and the same for vm8. And after that we return. Still, we want to clean up at this point because now we have filled in the data type vignette map, so we do not need the vm16 and vm8 here at this point. So if this is 0, then we delete the data from our memory. And next we have a for loop with int I equals 0, I is less than W times H, I++, and here we have vignette image, no, vignette map inverse. Now we need to fill in the inverse. Vignette map inf at position I is equal to 1.0 divided by vignette map at this position I. So 1 over the original value is the inverse value. Next we need to print something. Which is that we have successfully read photometric calibration. And I will also add this part here so that we know that this is all from the photometric undistorter. And this way it will be consistent. Reading from the file as well. Okay. Yeah. Mathematically not complicated, but a lot of work to do that and to manage the memory, but still quite easy to do. And of course, if we are through this constructor, we need to set the valid equal to true. Because this way we know that this is a valid, let's comment that here, means we have proper values for gamma response and vignette. Something like that. Okay, next we have the photometric undistorter. And we have the destructor, which is implemented using if conditions. If the vignette map is not equal to 0, then we want to delete the array vignette map and the same for the vignette map inf, where we delete the map vignette map inverse. So we need to clean up the reserved memory, and that is also the output. Delete output. What was the output again? I think we have not used it yet. Oh, it's the image and exposure. Okay. Image and exposure. But we have not filled that yet. So this is probably done somewhere else. Okay. Next we have the method void photometric undistorter. Metric. Unmap float image, which takes in a float pointer to the image. And here we define an integer WH, which is equal to W times H. Then we have a for loop, int I equals 0, I is less than WH, and I plus plus. And within here we have a float binf c, which I don't know what this is. We'll find out. And the float color is equal to image at position I. Next we check if color is less than 1e minus 3, so close to 0. If this is the case, then we set binf c to 0.0. Else, if the color is greater than g depth minus 1.01 f, then we want to set binf c is equal to g depth minus 1.1. Okay, so this seems to be some kind of clamping. Not sure why this is 1.1 and this is 1.01 f. Should rather be 1.01. Okay. Let's add a to-do. Next we have else int c is equal to color, float a is equal to color minus c, and b in c is equal to g at position c times 1 minus a plus g at position c plus 1 times a. This looks like a linear interpolation to me. Across neighboring pixels, maybe? B inverse C. What could this mean? B inverse C. Okay, C is probably color. Brightness inverse color, maybe? Not sure. Let's see what we do with that. So float val is equal to B inverse color. And if the value is less than 0, then we set the value to 0. And after that, we take the image at position I is equal to value. So we update the image. Of course, we need a semicolon here. This image is passed here. So we change the image data here in this part. Unmap float image. I have to admit I'm not sure what this means or what this does. Let's add this comment here. Why not 1.0? 1f. Okay, this will probably apply the vignette image to the image data. Where is this called, by the way? Oh, not yet. Okay. Then I know why I have no clue what this does, because it's not called yet. So let's see later. Now we need the process frame method. So this is the unmap float image, and we have a 3 times process frame, which we need to add here. So this is templated, a templated method, template, type name, T, with void photometric undistorter, process frame, template type T, pointer image in, float exposure time, and float factor. Like this. And this will be here 2 times as well, but without a template parameter. Oh, sorry. Of course with the template, but without the type name. But instead of the type name T, we have void. Like this. And we have no implementation. And we have the process frame as different data types, unsigned char here. And unsigned short. Oh, I forgot we already have the void. So I can delete that here. Process frame. Oh, of course, we need to change this one. Unsigned char. And unsigned short. Okay, but the magic will happen in this implementation. The other ones are probably only leftovers, I would say. I think we can delete them. Let's add a to-do. Oops. Oh, that's nice. Okay. Now let's implement the Undistort method. Not the Undistort method, but the process frame method, I mean. With int wh is equal to w times h. Float pointer to data is equal to output. And then the image, which is of type float pointer. Say image and exposure. Float pointer to image data. Okay, if we have that, we need to assert if we have correct values. So we check for the output w is equal to w and output height is equal to height. And we also need to assess the data, which cannot be equal to 0. And if this is passed, then we check if not valid, or the exposure time is less than or equal to 0, or we have the setting photometric calibration is equal to 0, in which case I think it should be rather like this. Disable full photometric calibration. I would change this to full photometric calibration disabled, i.e. perfect images. In this case, we have a for loop, int I equals 0, I is less than WH, I plus plus, where we fill in the data at position I is equal to factor times image in at position I. So this is just like a brightness change in my view. We have a factor, we multiply it with the image intensity. After that we say output exposure time is equal to exposure time, and output timestamp is equal to 0. So you basically combine the image in with the factor and set the exposure time and the timestamp. Not sure why the timestamp is initialized to 0. It should be a running number. I think I personally no, this would be wrong. But I would initialize the timestamp with like a count ID or something. So 0, 1, 2 and so on. But maybe it's not relevant for the operation of the Visual Slam to have a timestamp. So it's okay. Okay, else. We have a different for loop for int I equals 0. I is less than WH, I plus plus. Namely, this time we say data is equal to image in, but we take this as the position for G. Like this. So we say data I is equal to G at position image in at position I. Okay, now I can see how this comes into play. So G, it seems, is our irradiance. This is still a little bit weird to me. Why do we take G at position image in at position I? Image in is a template. This is a float. Okay, usually this would be nice to debug later, but let's continue. If the setting for the photometric calibration is set to 2, let me double check that. Oh, I mixed up. Photometric calibration is equal to 2. We do not have a 2 here. Setting photometric calibration is equal to 2. Ah, here's the explanation. 0 is nothing, 1 apply inverse response, 2 apply inverse response and remove vignette. Okay, but where's the check for 1? This is somehow weird. But maybe this will be applied somewhere else. So let's continue. Setting photometric calibration is equal to 2. Then we have a for loop. Int I equals 0. I is less than WH. If not standard is infinite. Vignette map inverse at position I. And then we have data at position I multiplied by vignette map inf at position I. Okay, and else we do the same. This is somehow weird. Okay. But here we basically remove vignette image or remove vignetting using inverse vignette map. Something like that. So we have the vignette map inf in the range of 0 to 1, and by multiplying it with the image intensity, we make it we have the inverse here. So we multiply it by 1 over the vignette image. So we basically divide it by the vignette image. Which will then lighten up the image data, I would say. multiply by 1 over vignette. Okay. So after we have checked if the setting photometric calibration is equal to 2, we say output exposure time is equal to exposure time, and output timestamp is equal to 0. And after this, we say if not setting use exposure, then we say output exposure time is equal to 1. All right. That's all about the photometric undistorter. Now for the distort class. Here we have undistort, the destructor. This one is defined as if remap x is not equal to 0, then we delete the whole array remap x. And if remap y is not equal to 0, then we delete the whole remap y. Like this. Next we have the undistort. Will get us a pointer to the undistort class. Undistort get undistorter for file. Standard string config file name, standard string gamma file name, and standard string vignette file name. Like this. And here we now print cout reading calibration from file config file name cstring and standard end line, of course. So let's read on the file. If ifstream input file stream with config file name cstring, if not fgood, then we close the file and we print something. It's not cout not found, cannot operate without calibration, shutting down. And then we make a new line. And then we close the file again. Return 0. Okay. Next, we print found, standard end line, then we create this L1 for line 1. We say standard get line from F into L1. And now we close the file. Next, we create a float array IC with 10 spaces, the size of 10, and an undistort pointer to U. Not to U, but to the undistort. And then there's a comment for backwards compatibility. Use RAD10 model for 8 parameters. So if standard scan F L1 C string with the format %F 1, 2, 3, 4, 5, 6, 7, 8 times, with the reference to IC at position 0, 1, 2, 3, 4, 5, 6, 7, 8. Like this one. And this is 0, then 1, 2, 3, 4, 5, 6, 7. If this returns 8, the scanf function, then we want to print something, standard cout, found RAD10, OpenCV, camera model, building rectifier, okay, so we have found the RAD10 model. So we set U is equal to new undistort, but not undistort, but undistort RAD10. Config file name, C string, and true. No prefix is true. Next, if not U is valid, then we delete U and return 0. So what we are doing here is we are parsing the config file name. We are looking in the config file name if the first line contains eight values. And if this is the case, we automatically assume that this is the Red 10 camera model. So we make a new undistorter of this type, pass it the config file name, and then we check if this has completed as a valid object. So if the file was read and if everything went well. And in this case, the object is valid. And if it's not valid, we delete U and return 0. Simple as that. Now we also need to check for the other types, other camera models. So we add an else if here and say for backwards compatibility, use pinhole or FOV model for 5 parameters. So this will be 5. This will also be 5. The rest will be the same. We need to delete the rest. Okay, this should be correct. But here we check if IC at position 4 is equal to 0. Then we say okay, let me quickly get this right. So if IC4 is equal to 0, then we have found the pinhole camera model and are building the rectifier. And the rest will be included here. Like this, we create a new undistorter of type pinhole. We pass it the config file name and true. Then we check if U is valid. If it's not valid, I mean, then we delete that and return 0. And else, we make the same. But this time we found the A10 camera model, building rectifier. I would rename that from A10 to FOV, because here we are using the Undistort FOV. Pass it the file name. We check if it's not valid, then we delete it and return 0. And this is the whole part. For the pinhole and FOV model. Next, we add an else if block. But say here, clean model selection implementation, whatever this means. But this will handle the Canalabrand, Rattan and equidistant camera models. So for Canalabrand we have 8 parameters. Again, let's copy that here. Okay, like this. Let's also print something to the console. This one is and the change is that here, in this case, the camera.txt file will start with canala brand, and then the 8 parameters will follow like this. Found canala brand. Here U is new Undistort KB with config file name, and the prefix this time is false. But the rest is as usual. So that is like this. Okay, and the rest continues like that for the other camera models. So here we have the RAD10 camera model with 8 parameters as well. So here we will create the RAD10 and need to adjust this output. Okay. Okay, so now I understand what this clean model selection. i.e. camera.txt starts with the camera model type. So now in this part we just look for the keyword here and then call the appropriate camera model undistorter. So if we copy that, we had the RAD10. Next is the equidistant. Equidistant. The rest is the same, even the number of parameters is 8. But now for the FOV model, here we have 5 parameters. 1, 2, 3, 4, 5. So this should be 5 in this case for the FOV model, and here we of course need to remove the 3 parameters, but the rest is still identical. And after the FOV model, we copy that, and then we have the pinhole camera model, which also contains 5 parameters. Here we have the pinhole, undistort pinhole, like this. And if everything fails, Then we simply print something. That is, could not read calib dot there's camera dot txt file exit. In this case we want to exit with the 1 as a status. But if it succeeds, then we say u load photometric calibration. We pass the gamma file name, an empty string, and the vignette file name. And then we return u. Now we need to implement this function or this method. Void undistort load photometric calibration standard string file standard string noise image standard string vignette image. Here we set up the photometric undist object to be a new photometric undistorter, which takes in the file, the noise image, vignette image, and get original size at position 0, and get original size at position 1. So let's break this. Okay, so after the, I think this was the constructor. No, get undistorter for file, okay. After get undistorter for file finishes, it will load the photometric calibration, which will create a new photometric undistorter object. And then the constructor is called and the data is loaded, the images are undistorted. Yeah. Okay. Next, we have this undistort method, which starts with template, type name, t, and we have an image and exposure object, a pointer. And we have this undistort method, which takes in a const minimal image of type t, pointer to the image raw, image raw, float exposure, and double timestamp, and a float factor. It's a const method. And after that, we'll create this method 2 times. Template, image and exposure. undistort. But here we have the type unsigned char. Constant minimal image with type unsigned char. And with no implementation. And here as well. But here we have unsigned short. And here, of course, unsigned short as well. And we are missing the template. So these are the three types due to different image types. But once again, I think only this one is really being used because the others are empty. So let's implement this one. If image raw width is not equal to width original, or image raw height is not equal to height original, then we see out that undistort wrong image size we have image raw W and image raw height instead of what? Instead of the W and H let's make a space here, or let's make an X. W and H, then we have this closing parenthesis. And an end line. Okay, what is wrong here? Should be correct. Ah, okay, I see. Instead of like this. And in this case, we exit with status 1. Else we say photometric undist process frame. Here we process the frame with the data type T. We pass the image raw, data, exposure, and factor. Then we have an image and exposure object, which is the result. A pointer, which is new image and exposure with WH and timestamp. And then we have the photometric undist output, copy meta to the result. So this will copy, I think, the timestamp and the exposure time to this result. It's a helper function, if I remember correctly. If not passed through, then we want to do something, actually a lot. Else we want to mem copy result image to photometric undist output image with the size of float times w times height. And at the end we want to apply blur noise result image. And then we want to return the result. Not sure why we want to apply the blur noise. This is interesting at least. So let's add a to do. What is this? Or what and why is this? We need to clarify that. The apply blur noise is not implemented yet, so we'll find out later. Okay, first of all, let's continue with the pass-through. So if it's not passed through, then we want to create a float pointer to out data, which is equal to result image, and a float pointer in data, which is equal to photometric undist output image. Then we have float pointers noise map x is equal to 0 and float pointer noise map y is equal to 0. If benchmark var noise is greater than 0, then we want to set some noise. Int num noise is equal to benchmark noise grid size plus 8 times benchmark noise grid size plus 8. So we initialize the total number of noise we want to add. We say noise map x is equal to new float with num noise as the size. Noise map y is equal to float num noise. Then we say memset noise map x 0 size of float times num noise. So we initialize the values here, noise map x and y. And then we have a for loop with int I equals 0, I is less than num noise, I plus plus, noise map x at position I is equal to 2 times benchmark var noise times random divided by float cast rand max minus 0.5 f. And the same is done to the y values. Okay, so unexpectedly, when we undistort, we add some noise. I think this might be a leftover from some tests. So let's add a comment. Not really sure, maybe it is supposed to be like that, but it looks like a quick way to add noisy images or to alter the images to be noisy. So here probably the real undistorting begins here. For int idx is equal to width times height minus 1. idx is is greater or equal to 0. And then idx minus minus. It's decremented. Here we get interp values. So float xx is equal to remap x at position index. And float yy is equal to remap y at idx. Now if the benchmark var noise is greater than 0, then we have a float delta x is equal to get interpolated element 1 by cube. We pass the noise map x. Then we have 4 plus xx over cast to float w org times benchmark noise grid size. And then we have the same for no, just a second. So here we have yy and the height original, and the rest is the same. And after that we have benchmark noise grid size plus 8. So this looks very cryptic, but we are getting an interpolated element with bicubic interpolation or bilinear using cubic interpolation. Then we have the same. Let's copy that. Delta y. Now we have the noise map y with w org. The rest is the same. Okay. So this is it. Next we continue with float x is equal to idx modulo w plus delta x, and float y is equal to idx over w of delta y. Next we add if x is less than 0.01. Let's write it in line. X is 0.01. We do the same with y. And now we check for x greater w minus 1.01. And here we say x is equal to w minus 1.01 and y is greater than h minus 1.01. Y is equal to h minus 1.01. And then we say x is equal to get interpolated element like this, remap x, y, w. We do the same for y, for wy. Remap y, x, y, w. Okay, after that, we check for if xx is less than 0. In this case, we say out data idx is equal to 0. And else, we say get integer and rational parts. Int xxi is equal to xx, and int yyi is equal to yy. Then we say xx minus 1 minus equals xxi, and yy minus equals yyi. And then we define a new float, xxyy is equal to xx times yy. Yeah. So those are the preparations to get the integer and rational parts. Rational parts, I mean. Next we get offset and check range. With integer source offset is equal to xxi plus yyi times w arc. Then we check that if source offset is less than 0 or source offset is greater than h arc minus 1 times w arc. If this is the case, then we want to say out data idx is equal to 0, but there's a comment from the original authors which says fix me, check why the offset is out of range. In the first place, there might be other places which access invalid memory. Fix the source. I will not do that because I think that's anyway just a benchmark part here. Oh no, this part is over. Okay. Yeah. Maybe I need to fix that, but for now, let's continue. Else we want to get array base pointer, which is a const float pointer source is equal to in data plus source offset. And now we want to interpolate using bilinear interpolation. So the out data is equal to at position idx, of course, is equal to xxyy times source at position 1 plus w_org plus yy minus xxyy, come on, times source at position w_org plus xxyy times source at 1. And here we have 1 minus xx minus yy plus xxyy times source at 0. And this is this. Then we have a check for the benchmark. If benchmark var noise is greater than 0, then we want to delete the array noise map x, and we also want to delete the noise map y. Then we have the else block. If we pass through, then we just copy the image data, we apply the blur noise and return the result. Okay, here we have coded already what we need. So we can now continue with the apply blur noise. So void undistort apply blur noise float pointer img const. Here we check if the benchmark var blur noise is equal to 0, then we return. And else we do we blur the images, it seems. Okay, let's turn on the music. So the var blur noise is 0 anyway. So I will I'm thinking about skipping this one. Oh well, no, let's continue. So int num noise is equal to benchmark noise grid size plus 8 times benchmark noise grid size plus 8. Then we have a float pointer noise map x, new float num noise. We do the same with the y. And now we have also a blood TMP, which is of size w times h. If benchmark var blur noise is greater than 0, then we want a for loop with int I equals 0, I is less than num noise, I plus plus, noise map x at position I is equal to benchmark var blur noise times rand divided by cast to float rand max. We do the same with the y noise map. Okay, that's actually it. Just initialize the noise map. Then we have a float Gauss map with 1000 values. Then we have a for loop, int I equals 0, I is less than 1000, I plus plus. And here we take the Gauss map at position I. Oh, you cannot see it, I'm sorry. Here we evaluate the Gaussian function, which is done by calling expf, exponential function, cast to float, negative I times I over 100 times 100. So this should be the standard deviation, I think. That's 100. So now that we have the Gaussian map, we set the X blur, which consists of a for loop with int y equals 0, y is less than h, and y plus plus. And we have the same inside, but for the x, if x is less than w, x plus plus. And here we say float x blur is equal to get interpolated element 11 a bicube with almost the same values as above. With noise map X, and we have 4 plus X divided by float W times benchmark noise grid size. The next line we have 4 plus Y divided by float H times benchmark noise size and benchmark noise size plus 8. So like this, semicolon. Then we have if X blur is less than 0.01, we set X blur to 0.01. So this is a clamping. Then we have an integer with kernel size, which is equal to 1 plus cast to int 1.0f plus X blur times 1.5. So this is the kernel size. Then we have a float sum w is equal to 0. Float sum cw is equal to 0 as well. Now we have a for loop. Int dx is equal to 0. Dx less than or equal to kernel size. Dx plus plus. And here we have an int gmid equal to 100 times dx over x blur plus 0.05 f. Then we check if gmid is greater than 900. Here we set the gmid to 900, so it's also some kind of clamping. And we create a float gw, which is equal to Gauss map at position gmid. Next we check for if x plus dx is greater than 0 and x plus dx is less than w. We need to check if it's in the bounds. And we say sum w plus equals gw and sum cw plus equals gw times img at position x plus dx plus y times this w. Next we have almost the same, but this time with the negative x direction. X minus dx is greater than 0 and x minus dx is less than w. But we add the condition and dx is not equal to 0. In this case we do the same, sum w plus equals gw, sum cw plus equals gw times img, x minus dx this time, plus y times this w. Okay, and after that we do a blood tmp at position x plus y times this w is equal to sum cw over sum w. Okay, so this was the X blur. Okay, but the comment is wrong, it seems. Oh no, it's perfectly fine. Okay, so this is the X blur. And we copy that and paste it and rename that Y blur. What is different here is that we changed int Y to int X, and X is less than width, X plus plus. Then we have int Y is equal to 0, Y is less than height and Y plus plus. And here we have a float for Y blur, get interpolated element 11, noise map Y this time. Then we have the same here as before, but this one here is Y blur is less 0.01, Y blur is equal to 0.01. Now the kernel size needs to be adjusted for 0.9f plus Y blur times 2.5. This is interesting. Different from X blur. It's interesting why this was chosen to be different. Then we have for dy, dy less than or equal to kernel size, dy plus plus. And we have gmid times dy and Y blur plus 0.5 this time. Okay, that's an error also in this part, so this is also 0.5. Sorry about that. Then we have gmid is greater than 900, then gmid is, there should be a single equal. There's 2. And then we have float GW, Gauss map. Then we have, this time we have Y plus dy greater 0 and Y plus dy less than h. Then we have GW and not times IMG but blood TMP of x plus y in parentheses y plus dy and this w. Then we have y minus dy is greater 0 and y is y minus dy less than height, and dy is not equal to 0. Then we have some w plus equals gw, and gw times, again, blood TMP instead of img. And then we have x plus, in parentheses, y minus dy times this w. And then we have not blood TMP but img again. X plus y times this w is equal to some cw over some w. Okay, after that, we want to delete the noise maps. Noise map x and delete the noise map y. Okay, next we want to implement the make optimal k crop. So we write void undistort make optimal k crop like this. Then let's print finding crop optimal new model. Standard end line. And then we say k.set identity. So we start with the identity. And then let's see if there's some kind of search method we will implement. Okay, so after setting the identity, first we stretch the center lines as far as possible to get initial course. In the original code it's written ques, but I think it's guess. Get initial course guess. So we want to get a first guess, it seems. Float pointer t gx is equal to new float 100,000. 100,000, yes. We make the same for the y value. And now we set up a float min x is equal to 0, float max x is equal to 0, float min y is equal to 0, and float max y is equal to 0. Now we have a for loop with int x is equal to 0, x is less than 100,000 and x plus plus. Here we initialize tgx at position x to the value x minus 50,000 dot 0f over 10,000 dot 0f, and next we have tgy at position x is equal to 0. This is the initialization. Then we distort the coordinates with tgx, tgy, tgx, tgy, and we pass, I think, 10,000. Is it 10,000? No, it's 100,000. 100,000. Then we have a for loop with int x equals 0. X is less than 100,000, I mean. X plus plus. If tgx at position x is greater than 0 and tgx at position x is less than w_arc minus 1, the original width. So we check for the bounds basically. If min x is equal to 0, then we set min x is equal to x minus 50,000 dot f divided by 10,000 here in this case. 10,000 0f. And after that we set max x is equal to x minus 50,000 dot 0f divided by 10,000 dot 0f. In the next for loop we do the same as we did at the above. So this is for x axis, I would say. We do the same here for the y axis. So we say int y is equal to 0. Y is less than 100,000, I mean. Y plus plus. And we have tgy and then tgx, both at position y. And the first one is y minus 50,000 divided by 10,000. Then we distort the coordinates using the same command of 100,000. Then we have int y is equal to 0, y is less than 100,000. And we have y plus plus. Y plus plus. Okay, now we need to change this. tgy at position y is greater 0 and tgy at position y is less than h original minus 1. And here if min y is equal to 0, then we set min y to y minus 50,000 divided by 10,000. And after that we have max y, y minus 50,000 divided by 10,000. And that's it. Next we delete what we have created. So tgx and tgy. And we take min x times equals 1.01, and we do that we do the same with max x. Then we have min y and max y. So we increase the range. And then we print something to the console. Which tells us initial range x print something here, which is min x max x min y and max y, like this. But we have x, we print min x, then we have dash then we have a semicolon, y colon, min y dash max y. And not to forget an exclamation mark and an end line. Okay, so this is the initial range. Next we continue with the comment. Second, while there are invalid pixels at the border, shrink square at the side that has invalid pixels. If several to choose from, shrink the wider dimension. Bool OOB left is equal to true. There's an OOB left, OOB right, which is also true, an OOB top, and an OOB bottom. Which is also true. Then we have an integer iteration, which is 0. So this looks like an optimization. And now we start a while loop. The condition is OOB left or OOB right or OOB top or OOB bottom. Okay, what we do here is the following. We say OOB left is equal to OOB right, is equal to OOB top, is equal to OOB bottom, and this one is false. Then we have a for loop with int y equals 0, y is less than h, and y plus plus. Then we have a remap x at position y times 2, and this is equal to min x. Then we have the remap x at y times 2 plus 1 is equal to max x. Then we have remap y this time, y times 2 is equal to remap y at position y times 2 plus 1, and this is equal to min y plus max y minus min y times float y over cast to float h minus 1.0 f. Next we have distort coordinates, remap x, remap y, remap x, remap y, and 2 times height. Then we have for, let's make a for loop here, for int y equals 0, y is less than height, and y plus plus. Then we have if not remap x at position 2 times y if this is greater than 0, and remap x at position 2 times y is less than w arc minus 1. Then we want to set OOB left is equal to true. Almost the same if statement, if not remap x 2 times y plus 1 is greater than 0, and remap 2 times y plus 1 is less than w arc minus 1. Then we say this is the right side, so OOB right is equal to true. And this will cause this while loop to break or to finish. So those are important checks. Now we do the same. So let's say here, maybe like this. Check for left and right bounds. And we copy that and paste it, because now we want to check for the top and bottom bounds. So we have this part for left and right. And then we have this part for top and bottom. So int x is equal to 0, x less than w, x plus plus, remap y, and remap x, x times 2, x times 2. Here we have min y and max y. And here we have remap x with x times 2 plus 1 is equal to min x plus max x minus min x times float x divided by float w minus 1.0 f. Then we distort the coordinates, remap x, remap y, remap x, remap y, and 2 times the width. And after that we do for int x equals 0, x is less than w, and x plus plus. Then we have if not remap y 2 times x, 2 times x is greater than 0, and remap y 2 times x is less than w original, I mean height original, getting confused. Time to take a break soon. So here we say OOB top is true, and if not remap y 2 times x plus 1 is greater 0, and remap y 2 times x plus 1 is less than h original minus 1, and here we say OOB bottom. So this means that the positive values go to the bottom. So the y-axis is oriented from top to bottom in the image space, which is something important to keep in mind. So now this for loop is finished, and after that there's a check if OOB left or OOB right and OOB top or OOB bottom. Then we check if max x minus min x is greater than max y minus min y, in which case we want to set OOB bottom is equal to OOB top to false, which means only shrink left right, and else OOB left is equal to OOB right, and this is equal to false, which means only shrink top bottom. Okay, now after this if statement there are some inline if statements for if OOB left. If this is true, then min x will be multiplied by 0.995. And we do the same for the other bounds, right? Top and bottom. We set min x, max x, min y, and max y. And then we iterate, or we increment the iteration, plus plus. And we then print something. Namely, we want to print iteration iteration number, the iteration x with range x, range x. Then we have this min x minus max x, and we have y with min y minus max y, and an exclamation mark and end line. I think I misspelled here something wrong. So this should probably be y and not the opening bracket. Okay, if cout, no, standard cout. Now we have an if condition, if iteration is greater 500. Then we want to print something again. Namely, that we failed to compute good camera matrix. Something is seriously wrong. Aborting. And then an end line. And of course we need to exit with code 1 because something is wrong. Okay, let's finish up this method at this point by setting the new calibration matrix. Use calculations from above to update camera calibration matrix K. So we say K at 0, 0, so the top left is equal to float W minus 1.0f divided by max x minus min x. And similarly, the bottom right, 1, 1, or this is actually the center of this 3x3 calibration matrix, float h minus 1 divided by max y minus min y. Then we have k 0, 2, just the top right is equal to minus min x times k 0, 0. And then the value below that, 1, 2 is equal to min y times k 1, 1. Okay. Now let's also add this method, void undistort make optimal k full. Unfortunately, this one is assert false. It is not implemented, it seems. Or it is not needed because for the full camera it's already given correctly. So let's add a to-do. Okay, and now unfortunately we did not finish, or I did not finish this whole file, but I need to stop the stream at this point. And I need to continue with the rest here in the next part. So in the next part we will continue with this read from file and then implement the actual camera models for distortion and for the undistortion. Thank you for watching and see you in the next part. Goodbye.